Have you ever stopped to think about how water gets from a reservoir all the way to your tap? Or how fuel gets from a giant storage tank into your car? Well, the answer, pretty much every time, is a device you've probably never even seen, but you absolutely rely on every single day: the centrifugal pump. They are the invisible, tireless workhorses of our modern world, and in this explainer, we're going to pull back the curtain and see exactly how they work.
Okay, let's just start with the scale of this thing because it is staggering. We're talking about a global market worth nearly $40 billion. So, right off the bat, you know this isn't some niche piece of tech. This is a fundamental, absolutely critical part of global industry.
And what's really fascinating is where all these pumps are going. Look at this. The biggest slice of the pie, almost a quarter of the entire market, is agriculture. That means these pumps are out there, right now, powering the irrigation that grows the food on our tables. And that's just one piece. You've got water treatment, oil and gas, chemicals. I mean, they are literally everywhere. So we know they're a huge deal, but how does a centrifugal pump actually do what it does? The genius of it is really in its simplicity. So let's break down the elegant physics that turn a simple spinning motion into an incredibly powerful flow. It all comes down to a force you've definitely felt before, maybe on a merry-go-round as a kid: centrifugal force. This is a great little illustration that shows the basic idea. Just imagine a can with some holes in it. If you spin it, the water gets flung outwards, right? The faster you spin, the harder it flies out. That's it. That's the core principle right there. Okay, so now let's upgrade from that simple can to a real pump. Instead of a can, you have this precisely engineered part called an impeller. See those curved veins? They're designed to just grab the fluid and sling it. And instead of open air, that fluid is collected by a snail-shaped casing called the volute. Those two parts, the impeller and the volute, they're the heart and soul of the pump. And here is where the real magic happens. So the impeller's job is just one thing: add speed. It flings the liquid out at a super high velocity. But here's the thing: speed alone won't push water through miles of pipe. You need pressure. And that's the volute's job. See how its shape gets wider, like a snail shell? That forces the fast-moving water to slow down. And when you slow down a fluid like that, its energy converts from speed into pressure. It's a brilliant and simple energy conversion. So you can see it's this beautiful continuous cycle. A motor spins the impeller flings the liquid out, which creates a little low-pressure vacuum at its center, what's called the eye, and that sucks more liquid in. The volute then catches all that high-speed flow, slows it down, and transforms it into steady, high pressure at the exit. It really just boils down to 4 actions: spin, fling, suck, and convert. But for all of its power and simple design, this machine has an Achilles heel. There is a destructive force that can literally tear a pump apart from the inside out. And this hidden danger is called cavitation. So what on earth is cavitation? Well, imagine you could make water boil, but without using any heat. Sounds impossible, right? But it can happen if the pressure in the liquid drops really, really low. And where's the lowest pressure point in the whole pump? Right at the eye of the impeller. If the pressure there drops too much, tiny vapor bubbles just spontaneously pop into existence. But here's the real kicker. The damage isn't done when these bubbles are born. It's when they die. As they get flung from the low-pressure center to the high-pressure edge of the impeller, these vapor bubbles don't just pop, they implode violently. And when thousands of these tiny bubbles are collapsing every second, they create these powerful little shock waves. To an operator, it can sound like the pump is chewing on gravel. It causes intense vibration, and over time, these shock waves will physically erode the metal of the impeller, literally eating it away until it fails completely. So how do engineers stop this from ever happening? They use a critical calculation called net positive suction head, or NPSH. Now, I know, it's a mouthful, sounds super technical, but the easiest way to think about NPSH is as a safety margin. It's the amount of extra pressure you have at the pump's inlet to make sure the pressure never, ever drops low enough for those destructive bubbles to even form. And this gets to the core challenge for any engineer setting up a system. You have 2 values to worry about. First, there's NPSH available. That's the pressure your system, your pipes, your tanks, gives to the pump. Then you have NPSH required. That's the minimum pressure the pump needs to operate without cavitating. And the golden rule is simple. What's available must always be greater than what's required, period. So avoiding cavitation is job number 1. But keeping these machines running reliably for decades, that takes consistent, smart, preventative maintenance. So let's take a quick look at how operators keep these absolutely critical systems in tip-top shape. It really breaks down into a simple rhythm. The first line of defense is just daily. You use your senses. You look for leaks, you listen for weird noises, you feel for vibrations. Then weekly, you're doing function checks, making sure backup pumps work and seals are good. Monthly, you break out the gauges, check pressures against the baseline, make sure everything's tight. And finally, you have the big annual inspection, a deep dive where you replace wearing parts like seals and bearings before they have a chance to fail. It's all about catching the small problems before they become huge, expensive ones. So where does a technology that's been around for over 100 years go from here? You might think it's pretty much maxed out, but that's not the case at all. The centrifugal pump is constantly evolving to meet the demands of the modern world. And you can see that evolution right in the numbers. This is not a stagnant market. From nearly $40 billion today, it's expected to surge to over $50 billion by 2030. That kind of growth is driven by real innovation. And the future really boils down to two big ideas, making these pumps smarter and greener. By putting in Internet of Things or IoT sensors, pumps can now predict their own failures. They analyze vibrations and temperatures to warn an operator weeks in advance. At the same time, there's a massive push to make them more energy efficient, which cuts down on operating costs and, of course, helps reduce their environmental footprint. So, the next time you turn on a faucet or fill up your car, just take a second to remember that unseen engine working hard behind the scenes. The centrifugal pump really is a masterpiece of elegant engineering, a simple idea scaled up to become one of the invisible, absolutely essential arteries of our modern world. And it kind of makes you wonder, doesn't it? What other hidden engines are quietly powering your life every single day?